Well, good morning. Sorry for the technical difficulties. We've overcome it pretty quickly. I wanted to introduce you to two NEAP proposals that is going to be under RC3. The first is going to be RC-3.1 for liquid metal cooled fast reactor technology development and demonstrations. And 3.2 is going to be for experimental validation of advanced reactor fuel failure. While we're on this title slide, I wanted to bring your attention down to the bottom right corner. While I am the federal POC on it, my name is Brian Robinson. I've provided my email address there. Two technical POCs for 3.1 and 3.2 are provided. Technical POC for 3.1 is Chris Grandy with his email, and 3.2 for Tanju Soku. Next slide, please. I'm going to go through these slides. There's not a whole lot of them, but one of the things that I wanted to encourage everyone is that when we get to these specific areas, to make sure that you have reviewed not only our objectives, our mission, and our applications that we're coming to, that we're developing for the NEAP, but also to take some time and look at some of the reference materials and some of the guidance that we've provided to make your proposals even more beneficial to us. Just to overview real quickly, the fast reactors, and specifically sodium fast reactors, is a long technology. We've been developing it in our country for 60, 70 years now. So some of the needs that we have are going to be much more specific to advancing that technology as we go forward. So let's go through the missions. Mission: perform targeted research and create sustained testing infrastructure to support demonstrations of U.S. fast reactor technology and to enable subsequent commercial deployments. As many of you know, the ARDP, Advanced Reactor Development Program, has launched, and we are in the throes of supporting that as we go forward. Those are going to be really big things for us. Sodium fast reactors is one of them, and getting that information and having it move forward is going to be very, very valuable, not only for the R&D, but for the human infrastructure, the capital, and the physical infrastructure that's going to be needed to support these advanced reactors. So our objectives: research, development, demonstrations of innovative cost reductions and performance enhancing technologies. 2, developing and sustaining a flexible domestic infrastructure and knowledge base for R&D and demonstration of fast vector systems. 3, clarifying fast reactor licensing framework and developing science-based approach for regulatory compliance. The facility that we're showing here is metal. Some of the proposals that we will be receiving and be testing some of the R&D in will be this facility. The POC here, Chris Grandy, provided this just to give a little overview of it. That is very interesting for those of you who have not seen it. Next slide, please. Major program R&D areas. For the commercial deployment of fast reactors, stakeholders have identified 2 recurring challenges. Capital investments is a dominant cost, and a pathway must be established for licensing non-light water reactors. Now, many of you may be aware that we are working on these things to reduce our cost and to work towards Part 53 with the NRC. So this work is continuing as we're going forward. So again, if you want to understand more of this, please reach out to the technical POC to make sure your applications are very aligned to the ongoing work and the supportive work that will be needed. To address these challenges, the program uses input for key stakeholders such as the industry-led Fast Reactor Technology Working Group to focus its efforts on the following high-priority R&D areas: preserving, streamlining access to, and qualifying legacy DOE fast reactor R&D and operational data for use in industry design and licensing cases. 2, industry outreach, developing more effective R&D. 3, utilizing metal facility to demonstrate these innovative components and instrumentation. 4, improving, sustaining, benchmarking, and validating existing fast reactor design and safety analysis. And the last one, providing the technical basis to support ASME qualifications of advanced structural material for use in fast reactors. More specifically, we're going to dive into 3.1 and 3.2 on these next few slides. 3.1, again, is liquid metal cooled fast reactor technology. We're seeking proposals to develop experiments, instrumentation, control strategies, and performance-enhancing technologies that have the potential to subsequently be deployed in U.S. liquid metal fast reactor concepts and could be demonstrated in metal. Focus of the technology, enhancements and experience work that can offer potentially significant benefits in reactor capital or operating costs. These examples could be development of test articles of metal, enhancement of advanced sensors and instrumentations, testing components for innovative liquid metal cooled reactor self-actuated control systems, shutdown systems, and the last one, experiments for in-service repair technologies. Slide 5, please. Examples to continue improving the performance of metal sodium technologies, including rugged high temperature resistance heating systems, improving insulation technology, improving sodium leak detection, and identifying technologies. Vessel support technologies that reduce heat loss, improve clamp-on flow meters, thermal monitoring, smaller and more compact refueling, etc. So there are a variety of things that fall under this one. Again, I would ask for those who have questions to address them either after this call or to Chris Grandy to get more specifics. And the last one, development of deployable sensors and prognostic techniques for demonstration in metal. We put a note here at the very bottom of this. This is the last slide. The proposal that limited examples work above. Applicants should include how their proposed work will support current DOE National Laboratory and U.S. nuclear industry liquid metal cooled fast reactor deployment commercialization. So we've also provided a link at the bottom of this so you can get more in-depth knowledge through metal. And I would also ask for people, I did not put it on the slide, but it's kind of an intuitive for people who are involved in it. You could also do a deep dive into OSTI. OSTI is a place where it's a database, a hub for many of our reports and data, and you can get an example. If you're pitching something or if you're proposing, you have a concept, you could go there and kind of work out what's been done and what needs to be done to go forward. But again, I will tell you, reaching out to the TPOC is as vital and important as anything else. So that's it for 3.1. We're going to roll over straight into 3.2. So our RC-3.2 title is Experiment Validation of Advanced Reactor Fuel Failure Modes. We only put one slide on this. The POC for this is going to be Tanju Sofu. Him and Chris are, I'm sure, on the call and can address questions after we're done. We're seeking proposals for university-led experiments to test the impact of cladding failure in fast reactor fuel assemblies for validation of fuel damage propagation models. Now, again, the SFR campaigns are very long in developing, and that's why this is a much more specific. We're not talking about low TRL technology readiness level. We're talking about advanced technology readiness levels, and we're trying to mature them to a point to ease some of the commercialization process. The focus of what happens when cladding fails and fission gas is released into the coolant channel under accident conditions. And we've addressed 4 areas here. Assess the impact of fission gas jet penetration, including potential flow, stagnation, or reversal. Evaluate degraded heat transfer conditions due to fission gas jet impingement on neighboring fuel pins. Transient overpower and loss of flow accident scenarios. And the last one, experiments with liquid metal coolants are desired. Other surrogate coolants are accepted or acceptable if appropriately scalable of the tested configurations for the liquid metal coolants that are being demonstrated. So with that, we have concluded the fast reactors sections 3.1 and 3.2. I would like to table it now for any questions.
Thank you, Brian. We do have a question so far. Everybody, please use the question answer feature of GoToWebinar if you do have a question on 3.1 or 3.2. And then after the webinar, we are doing a new process where you need to send your questions to neup@inl.gov if they're not answered at this webinar. So, okay, first question. For RC-3.2, which coolant is the focused, sodium or lead? And also, which type of experiment is preferred between high-resolution data using surrogate coolants or prototypical conditions? Thank you.
All right, I'm going to ask for Tanju if he's on the line, to address these questions. Tanju, are you available?
Can you hear me?
Yes, we can hear you. Yes.
Great, yeah. I think we're interested in both sodium and lead coolants. The need for fuel propagation, damage, fuel failure, damage assessment potential is of interest for both SFR and LFR concepts. The other second question is, I think the preference would be prototypical conditions. The fidelity of the data may not be of a major interest. If we can somehow characterize flow stagnation or flow reversal and the depth of jet penetration in an assembly, we don't particularly need CFD quality measurements for that. We do, however, value the impact of fission gas jet impingement on neighboring fuel pin surfaces, because that's essentially the key factor in understanding the damage propagation potential. So there, a detailed assessment of heat transfer degradation on the neighboring fuel pin surfaces would require some detailed measurements.
Okay, thank you. Next question. Is there a type of sensors which are of interest in these calls?
I think this is for Chris.
Yeah, so can you hear me?
Yes.
Yes, we can hear
So
you.
it would be the sensors that would go into a typical LMR. So it could be a flow sensor. It could be a sensor to measure elevation of the coolant. It is those types of sensors. So if you look at what the instrumentation that you would normally put into a LMR type of plant, those are the sensors that would support industry, if you will, right? And the commercialization of the technology. And those are the ones that we would be interested in testing. Thank you.
Great, thank you. At this time, we don't have any more questions for 3.1 or 3.2. Oh, wait, hang on. One just came in. Let's see. As a follow-up question on 3.2, can we use other liquid metals in a university laboratory since sodium and lead are challenging to handle in a lab? Would that be acceptable?
Yes, I think using other liquid metal coolants like gallium would probably be quite suitable for that purpose. again, we would be interested in some scalability study to demonstrate that.
Okay, thank you. Does development of advanced sensors for liquid metal environments include innovative neutron detectors?
Well, I would say, so this is Chris Grandy. So I would say that it would, but typically those detectors don't necessarily see sodium. So, you know, the focus of RC 3.1 is on alkali metal or liquid metal technologies per se that are actually immersed in the coolant itself. And the NIs are typically either ex-vessel or they're in a thimble inside the vessel. Thank you.
Okay, thank you. It looks like that's the end of the questions for this first portion. So Brian, when you are ready, you can go ahead with IRP NEAMS 1.
Great, thank you. Yes, good morning. Thank you for attending our NEAP CINR this year, FY22. This is going to be a little bit different of a presentation. I am providing the NEAMS presentation on behalf of a collaborative effort with Dave Henderson. The TPOC, technical point of contact on this, will be Chris Stanek. He will be providing any sort of information to people making proposals. And again, I would encourage people to reach out and get the specific details and walk through what your proposals would be with Chris. Dave Henderson and myself will be working very closely together to support the molten salt reactor and the development of the data that's going to be not only matured, but ultimately being able to support codes as we go forward. Slide 2, please. Acceptable levels of impurity in fission products in molten salts. The background, goals, and gaps. We'll go through these very quickly. The background, during operations of an MSR, impurities in the grow-in of fusion products collected in the molten salt coolants affect the thermal physical properties of the salt, corrosion kinetics of structural materials, and ultimately reactor operations. Our goal is to develop impurity limits guidelines and halide salts based on experimental and computational methods. One of the ways that we want to fill this gap is to develop guidelines, values, recommendations for the allowable concentration for impurities. Examples are oxygen fission products, actinides, and including evaluation of these components. All of this is to ensure sound MSR operation with a focus on heat transfer, containment, corrosion, and burnup simulations. More specifically, next slide, please. We'll talk about the fundamental corrosion mechanisms of austenitic stainless steel, ferritic, martinistic stainless steel, and nickel-based alloys. The background, goals, and gaps are as follows. Corrosion of stainless steel and nickel-based alloys in contact with halide salt is derived by the leaching of chromium from the alloy matrix and the formation of stable chromium fluoride or chromium chlorides at the salt containment interface. Corrosion rates of stainless steel and nickel-based alloys could be derived from chromium self-diffusion from the alloy matrix to the surface and the ultimate formation of stable chromium halides. Our goal is to create models of chromium diffusion and subsequent modeling of corrosion of austenitic stainless steels. We've provided some examples of the ones that we were looking at. And nickel-based alloys. So these are provided here. More specifically, we're looking, it doesn't include just these materials, but they're ones that are recommended by many of the manufacturers: 316, alloy 709, HT9 291, Hastelloy N, and Haynes 244. How we're going to fill these gaps? By having a fundamental and theoretical experimental basis for enhancing the current knowledge on corrosion of austenitic stainless steels or ferritic, martinistic stainless steels versus the more expensive nickel-based alloys in contact with halide salt melts at temperatures related to MSR operations. Very short presentation, but very deep in the two areas that we're looking at for levels of impurities and impacts on materials. With that will be our last slide. I'm going to test to see that Chris Stanek and maybe Dave Henderson are on board, and then push this back for any questions.
Yeah, I'm here, Brian. Happy to answer questions.
Great, thank you, Chris.
Dave Henderson is as well.
Great. Okay, let's see if we have any questions. Yeah, I think there's at least one here. Okay, first question. Should this corrosion study be specific to molten salts?
Yes.
Yeah, I'm stumbling on that because yes, and the variants of molten salts can differ, but yes, it needs to be specific to molten salts.
Okay, great, thank you. What is the expected balance between modeling and experiments?
This is Chris.
Chris, did you want to?
Yeah, I'm happy to field that one. I don't know that we necessarily want to prescribe that balance. I think the call is states that there's an openness to both experiments and modeling and simulation. And just to reiterate what Brian said, this is really a collaborative effort in a programmatic sense between the MSR campaign and the NEAMS ModSim program. So the expectation is that proposals will include both modeling and simulation and experiments, and I think it's up to the proposers to determine what the right balance would be.
Yeah, correct. I would also add the relationship to experiments and modeling it can be put in two different ways. You can use experiments to do predictive modeling, and then or you can do modeling to do predictive experiments. Both of those are acceptable. You just need the proposal needs to be clear on their path and what would be the benefits of doing one to the other. I will tell you that we are looking for both. Having something that is just down on a modeling without experiments is going to be kind of an issue, because we want to be able to mature the MSR program, and we find that to be having both of those to be very, very valuable.
Okay, is there a preference as to chloride or fluoride salts?
There is not a preference. They do, depending on how you're using the fluoride and the chlorides in either fast or thermal applications, there are benefits from one to the other, but we don't have a preference. It depends on what the proposal recommends coming to the table. Chris?
Yeah, I agree with that. The only thing I might add is that the impurities might be somewhat different. Obviously, when talking about fluoride, if the proposal was to focus on either fluorides or chlorides, it might be that the set of impurities would be necessarily different. But no, there's not a stated preference between which halide is the focus.
Okay.
If I might add, one other point. This is Dave Henderson. At least the scope as written currently, which could change. I think that's a disclaimer on any of the scopes in the current CINR draft. So pay attention to what gets made in the end. But the way this is currently drafted, we do have a statement that says industry partnership is required as part of this IRP. So that should be factored in as well.
Great, thank you. Next question. Should the corrosion effort also have a focus on the impact of fission in products or fission products and impurities?
Chris, I'll let you table that one.
Yeah, sure. I don't want, again, I don't want to be too prescriptive, but I think those two slides that Brian just showed, if to me, a compelling proposal would do a good job of linking those two concepts. So I wouldn't go so far as to say it's mandatory, but I think it would be very interesting to see if there were impacts of certain impurities, whether it's a fission product or something else, on corrosion rates and mechanisms.
Could investigating corrosion in salt under irradiation conditions be a consideration here?
Absolutely, yes.
Yes, I was going to go first, but yep, I agree with Chris completely. Yes, our reason for not making it too specific is we were trying to make a broader call, but that is certainly something that would be accepted.
Would surrogate impurities make the experiments easier to be a consideration?
Chris?
Yeah, I would say it depends if a compelling case could be made. I mean, obviously, experimentally, some of the fission products or actinides of interest might be very difficult, if not impossible, to consider, and especially in a university setting. So if a surrogate was to be proposed, I guess my recommendation would be to make a very compelling case for the selection of that surrogate, and make sure that it was translatable to the actual impurity.
Yeah, and I would add that, yes, there's nothing wrong with using surrogates. I think the application, to Dave's point earlier, more specific to commercialization would be the issue. So if someone's going to use a surrogate, having it mature into maybe a space where it can mature to support commercialization beyond just using a surrogate would be something I would look into. But yeah, surrogates are perfectly fine right now. It's just that once you start working towards commercialization, that's going to kind of minimize the advantages of using a surrogate. Thanks.
Okay, thank you to our presenters. It looks like that is all the questions that we have for this session. And so just as a quick reminder, if questions come up later, please email them to neup@inl.gov. And we will resume at 12 p.m. Eastern Time with the NEAMS Workscopes. Thank you.
Thank you.